Hello, hello. Can you hear me now? And are you able to
Sir.
see my slides?
Yes, sir.
Okay,
Yes,
okay.
yes.
Let's move forward. And voice?
Okay, sir. But
Okay, okay.
now able to listen.
Okay, we can forward.
Yes.
Okay, let's see. First question is extracted power from a solar cell can be maximized by. Option is given here. Minimize shunt resistance, maximize shunt resistance, minimize series resistance, maximize series resistance. What could be the answer?
DNC.
And why? You have to write in exam proper reason if asked.
Sir, if we minimize the series resistance, then VOC will not drop. And because the maximum power extracted is the formula of the VOC IC, VOC into ISC into field factor by power input.
Yeah.
Okay, we fix power input is fixed. Okay, but
Mm.
if we increase the sound resistance, then VOC will decrease. So as a result, we have to minimize the series resistance.
Yes, yes, yes.
VOC will increase. That's why we are current also. That's why we increase the series resistance. Decrease the value zero. And for shunt, for the if there is a trap resistant recombination impurities present there, there may be a recombination. That's why current will be ISC to minimize the ISC, increase
Okay.
the sun by increasing the sound resistance.
Let's see. Okay, you are right. But let's see in graph. We know the IV characteristics. Yes. So where is the series and where is the shunt in graph? Can you see? Which side is series and other side is shunt.
Sir, your skin is very small.
Wait. Now.
Okay, sir. Okay.
Okay.
Sir,
So
now tell me what.
oh, in IV characteristics, there is a graph like that. This is the ideal curve. Okay, this is axis is a applied potential. This is the current density axis. Here is the JSC, short circuit current, and here VOC, open circuit current voltage. Okay, if we if our curve has like that and one more like that and like that, then this is the shunt resistance
Yes.
decreases. Sorry, not increases. This is tell us shunt resistance RS decreases. If RS shunt resistance decreases, then what will happen? Our fill factor, we can see fill factor is reduced. Can we see?
Yes, yes,
Yeah.
yes.
Uh,
Area is big.
red curve area is like that a unity maximum. If area is decreases means fill factor is decreases. So power I into V is give us power. Yes. So basically here J into V. If divide by area multiply by area J, then we can calculate I. So this is J nothing like that I if we multiply. So this curve give us area or power. Area of this curve what we get? Power. So if area is decreases, then power is decreases. So we
Yes.
have to maximize power. Yes. So curve should be like that. One like that.
90 degree.
So what is the B maximize shunt resistance? So shunt resistance maximize like that. Control series and shunt. So shunt resistance increase like that. So shunt resistance should be maximum. Okay. Then minimum series
Sir,
resistance. Yes.
sir, sir,
Yes.
sir, during sun resistance, sir, the
Yes.
current is increased and VOC is decreased.
VOC will decrease. This is a
Sir,
rough
current
diagram.
is
This is
increased.
the
No, no,
uh,
no, just
this is the rough diagram.
okay, sir.
Okay.
During
Yeah. I am telling you idea how center and series relay affect the curve. Nothing else. And then what is the second point? Minimize series resistance. How? Series resistance, which side? This side, this side. Series resistance, if decreases, then curve like that. This is the series resistance decreases. Then obviously we can see area of this curve will reduce if series resistance
yes,
increases. So series resistance should be minimum and shunt resistance should be maximum. This is curve plotted by me experimentally. I I made device in lab at IIT Kanpur and
sir, what is RPM?
let me spin coating. You know spin coating. Solution is dropped by
Oh,
like that, and there is a our spin coater. This is rotating like there is a substrate. Our FTO or FTO with ETL layer, then perovskite. I have coated perovskite, then HTL and electrode contact, gold contact. This is the structure like that.
yes.
Okay, so I have optimized RPM. RPM, what is role of RPM here? RPM nothing gives. Uh, if the speed is maximum drop, if the drop is RPM 3000, speed is low less, then is uh, spreading is like that. If the RPM is maximum, then spread is more, and our solution is out of substrate. So means RPM is increased, then thickness of the coating of the solution will decreases. If RPM is increases, then thickness of our coating material will, if RPM increases, thickness decrease inversely proportional to
Yes.
RPM is max, then thickness will decreases. So in lab we have to optimize RPM, solution concentration, so many things. What is the timing of temperature? What is the time of rotation? Okay, so you can see a nice curve of IV. First curve is uh, 5000, then 4000, then 3000. Please tell me which curve is good, which curve has more fill factor, IV, VOC, JSA. You can see 3000 is
Is
3000 is better. Yes or no?
is
So,
is more.
hmm. So RPM 3000 RPM is good for me. Okay, because our parameter of solar cell JSA, VOC, fill factor, as well efficiency is more. Okay, let's move forward. Second question is solar cell having band gap of Ag1 and Ag2. Ag1 is greater than Ag2 are eliminated by one sun radiation. Then which of the following is expected to be true? Consider only optical losses. Here is only optical loss, nothing else. Please tell me which could be the answer in following option. Band gap. Let's see what is the band gap. We have a two material. H1 is greater than 2 H2. This is Ag1. This is Ag2. Ag1 is greater than Ag2. Okay. Then VOC and current. VOC directly related to the band gap. You know? On,
So yes, yes, sir.
yeah.
VOC2, VOC1 is greater than VOC2.
So then
When
VOC
the
VOC2
increases
VOC1
greater than
wait
greater
wait
than VOC1.
like that.
No. Opposite. VO, sorry, yes, yes, yes. Okay.
This is right now.
VOC2 less than VOC1.
This is
Ah,
right now.
another option will go in. Wait, sir. Another one.
Okay. I am
Uh,
waiting.
Yes. JC1 greater
Let's
than JC2. Yes.
why why are you thinking like that?
This only optical loss, no temperature
This
dependent.
could be the valid reason. You can see in diagram. Only the applied potential bending if not consider like that curve of the IVF. We know that there is a Fermi level
Yes.
inside. So first option is right. Then please tell me second with appropriate reason.
J1 less than J2
The answer is
greater
B
than
and
J1 less than J2 because during high band gap current will less in EG1 or band gap is high.
so uh, our solar spectrum like could be like that. one is not like that. Let me do it properly. Maximum is around 5,000. Then peaks and peaks like that. Consider this is invisible range wavelength in nanometer. So why this? J1 is less than J2. We know that if the solar spectrum is incident like that, if the band gap is less, then what is the uh, h nu? If greater than the band gap is E, then photon can be absorbed by material. Yes or no?
Yes.
Yes. Then uh, what is the if the energy is higher, then also is absorbed. But if the photon incident like that is to material photon incident of photon having energy is to then material first
Good,
is not
good
absorbed,
energy.
it's not absorbed,
Yes, yes.
so there is no
It's good
current.
energy. Yeah.
Okay, so I don't understand.
Yes, yes.
So can we move forward? Are you clear?
Yes, sir.
Okay. Third question is about shunt resistance in the solar cell can be increased by. We have to increase shunt resistance for maximize the fill factor.
VNC.
Yes, we have already said
VNC.
B and C.
NC.
Okay,
Yes.
yeah, you are right. Reducing the density, defect density in device. If there is no defect density, then obviously shunt resistance is increases and non-radiative recommendation should be. Okay, so this is the straightforward. Fourth question. Which of the following is correct for an ideal IV curve for a solar photovoltaic device? Answer is
This
already
MTF extensor.
uh, answer is
Yeah. Okay.
already there, but why this? We have to.
Yes. I want the explanation. Yes.
Yes, yes. Let's see. There is a IV curve. Okay. There is a V. This curve is J. We have to derivative and take the inverse. Here is a VOC. Here is the JSC.
Yes.
We have to derivative at G. First is V equal to VOC. We have to derivative at here 1 point, and another is V equal to 0. When? Where is V equal to 0? This V equal
Yes.
to 0 and V equal to VOC. Please derivative. This is the like that take a line V equal to uh, let's say Y equal to X. We have to put like that. This wait. So what could be the equation for this curve? Straight line. This is the fixed value. This is the fixed value like that 25 or something else milliamp per centimeter square if consider the area J. Let's say J equal to, okay, then divide take the derivative. This is JC is a fixed value. We know that. Take derivative. What could we get? 0. Yes or no? Yes or no? Constant, derivative of constant 25 with respect to v could be 0.
G.
Yes.
Yes.
And then
Yes.
take the inverse of this. This is at v equal to 0. Yes or no? Take
Yes.
the inverse 1 upon 0. Infinity. Inverse of this infinity. So this is right.
Okay.
Yes, clearly.
Yes. Yes. Yes.
Please calculate like that. D. You have to 5 minutes. I will be coming in 5 minutes. You have to think. You have to curve. You have to solve like that. Yes. Are you able to? Hello. Are you able to solve B option? Oh, D option.
Yes. And the we have to value is infinity. So correct. High value. So infinity of some derivative it should be zero. That inverse.
Okay. Let me solve.
Yes.
We have to take derivative where and here.
Answer.
So v equal to VOC. What could be the value of JC here? 0. Yes. We have to take derivative
Zero.
is equal to VOC. So 0. What it get? 0 or else.
Zero. Derivative.
0. Then let's put in another way. Not fix the value. We have to We have to take derivative, but we have to put a equation. First point is calculate, then what is the equation? We have to take derivative here. If the slope like that, actually we have to calculate slope at v equal to of this curve.
Sir, same thing, na, sir. We taking derivative in where v equals to 0
Yeah,
and the straight line towards the views.
yeah. Slope, what will be the slope here?
Straight line.
A straight line.
Just straight. Yes.
Yes, at curve. Inverse of this slope 90 degree. This is slope is 90.
Right.
Yes. So 90 slope inverse tan theta dv by dj by dv give us tan theta. If theta equal to 90, put the value of 90,
Undefined. Undefined.
tan 90
Undefined.
undefined.
Infinite.
Take inverse
Yes. 0.
0. Are you able to now understood?
Yes, yes, yes.
Okay, 0.
Thank you,
So
sir.
we have to think like that here. Actually, we
Yes,
have to
yes.
calculate in both case slope. Here is the slope 0. Uh, so tan 0. First case is tan 0. Second case is 90. Tan 0 0. Take inverse. In 0 inverse is infinity. Okay. Both cases clear.
Yes, sir. Yeah.
Okay. Okay. Let's move forward. Fifth question is which of the following statement is are correct for the polycrystalline silicon in comparison to single crystal silicon? Polycrystalline and single crystalline. We have to compare. So, what could be the answer?
Small carrier diffusion line. Polycrystal.
Okay, then one more is
Diffusion is low.
yes, highly depth
Defect.
density.
Yes, sir. Yes, sir. Yes, sir. Due to grain, some defects are there. Yes,
Yeah,
yes.
yeah.
Yes. I was wrong.
Smaller carrier diffusion length also.
Okay.
This is forward start forward nothing.
Yes, yes.
Next question is in a top illumination solar cell, light coupling can be enhanced by top illuminated solar cell. Light coupling can be enhanced by option is making bottom
Actually,
layer,
uh,
making top layer thin,
extending and
yeah,
C and D.
using
C and D.
anti-reflection coating.
Yes.
So anti-reflection, if we apply anti-reflection coating, then light is reflection is less. So efficiency or is more. And texturing is also minimize the optical losses. Yes or no?
Reflection.
Yes.
Yes. So texturing means
Yeah, let me.
the 111 and 100 by
No, no,
doing
no,
top
no,
layer
no, no, like that.
texturing.
We have to like that.
It's reflection.
If light is incident like that, then reflect, then inside not. So we have to set the angle value, but minimize the loss. That incident like that, then not go, then go inside like that. Okay, we have to ensure normal minimize the losses of optical losses by texturing. Also anti-reflection. Let's move forward. Which of the following is are favorable for different efficient silicon solar cell? Efficient silicon solar cell. Heavily doped base and heavily doped emitter
C, first C, large diffusion length of minority carriers
and
and large
large
electric field. Yes,
built-in electric field
very
also should be large.
yes.
If the efficiency is higher, then built-in electric field is also high and large diffusion length.
Hello,
Okay. Yes, yes,
hello.
yes. Are you there?
Yes, sir. Yes, sir.
Okay, okay. So clear?
Yes.
Let's move forward. Which of the following strategies are adapted to improve the current collection from the top of silicon solar cells? Answer. What could be the answer?
Oh, sorry, sir. I was in just phone call. Okay.
Okay. Please uh, read the question and tell
Yes,
me
sir.
the
Yes.
answer.
Yes. Which are the following? The answer B and B and D.
Didn't take long. Okay. B and D.
B and
Yeah,
D.
yeah, you are right. Heavily doped near contacts and deeply buried contacts. This is about the contact. Let's move forward. Yeah, the correct sequence for the generation of electricity in solar cell is first is absorption, then diffusion of charge carrier to
D. Number
electrode,
D.
number D. Yeah, material first absorb the light, then create the exciton, electron holes, excitation and diffusion of charge carrier, move to the respectively electrodes and collection of charge carrier at electrodes by external circuit like that. Then we will get VOC, which is like okay. This is optional. The method adapted to reduce the surface recombination in silicon solar cell is
Surface passivation.
okay.
One B.
Reduce the surface recombination. B
Surface passivation.
and heavily doped rear surface of the cell. If the we have to dope the heavily, then also minimize the recombination.
Sir, how sir? In if we go heavily, career lifetime will decrease, na sir?
Carrier lifetime
Will decrease. for uh, inversely proportional
Yeah,
doping.
uh, rear surface.
Top
This is
surface or bottom?
bottom surface.
Rear means
Bottom
bottom.
surface.
Oh, bottom. Yes, 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 yes. Bottom surface. P plus. Yes, yes.
Okay,
Sat
this
told. Yes, yes,
the front side surface is uh, top surface.
yes,
Rear
yes.
surface.
Yes.
Then it's some layers. Okay, then move forward.
Sir, sir, one question.
Yeah,
Sir, sir, why we make top surface thin due to high doping level? We make the surface thin.
thin. We have to penetrate the light also. The charge carrier is generate more. Cross. One more thing is crossing the charge carriers to the electrode.
Junction, towards junction.
Yeah, in silicon solar cell, this is the case, but in perovskite, not. Perovskite is
Yes, correct. I don't know.
perovskite is different mechanism.
Yes, yes.
In perovskite, let me tell. I will tell you in last. Okay.
Okay, sir. Generation 3.
Okay. Which of the following is are incorrect for multi-crystalline silicon solar cell?
Soul sets like
Large number of grain boundary for multi-crystalline.
not soon. Now it's multi-series are
Okay, now visible.
supposed to. Yes, yes, yes.
Oh, let please read. B option is low number of grain boundary for multi-crystalline silicon solar cell. Grain size is larger than the device thickness. Grain size is smaller than the device thickness. Obviously, we know that the grain should be grain.
Multi-crystalline, yes, sir. Sir, 1 minute, I tell you.
Okay.
Multi-crystalline. Mm. Grain size is smaller than divide thickness
Yeah,
first.
obvious.
Multi-grains are there first.
Yes.
And large number are yes, large grain.
In multi-crystalline, grain boundary is higher or more
Yes.
like that.
Sir, here recombination is high, na, sir? Multi-crystalline.
Yes.
Due to grain boundary traps are created.
Mm-hmm. And
Yes.
grain size could not must be
Smaller.
must be smaller in multi-crystalline. Okay. Cannot be greater than the device thickness, grain size. Grain are smaller, obvious. Let me let forward. The passivation of the Dandling bond in the amorphous silicon solar cell is done by
Reduction.
a slide as visible.
Yes, I know. Without the right things.
What?
Hydrogen passivation. Hydrogen passivation.
Okay.
Yes.
Dandling bond. You know the Dandling bond. Dandling bond. Where is the Dandling bond? Inside or surface? If the material like that.
One atom missing, one electron missing.
Dandling
One.
bond at present surface like that.
Yes.
Then hydrogen bond attach is to H bond is to O bond. like that oxygen. Okay, so that's why passivation passivation we have to passivate the surface dielectric bond by making hydrogen bond at surface. 13 question. Silicon nitride coating on the emitter in polycrystalline silicon solar cell is done to.
Sir, reduce surface recombination.
Okay, reduce the surface loss, reflection losses. This is the anti-coating silicon nitride. Like so, reflection losses could be reduced by coating anti-coating. Okay, what is the
Sir,
use of
one thing, sir.
yes?
Sir, SATs in lecture told that use of impurities done by titanium and passivation with hydrogen. Okay, this A silicon. Okay, okay. Correct, sir. This is A silicon. আমার
Okay,
to- Okay, sir.
then yeah, this is the last question of the today session. Please read. This is the numerical question. Are you able to see? Not yet.
No, no.
Wait. Yeah. Now,
Yes,
yeah.
yes.
A solar cell deliver a short circuit current under 1.5 mm. The reverse saturation current, open circuit voltage, neglect any internal thermal losses. Internal resistance of the solar cell would be. You have 5 minutes. Please calculate.
I see. So reverse saturation current I zero 10 20, 11 ampere. Which I
10 to 11.
V naught
10 to 11.
10 to 11.
Yeah.
What is called VOC plus to KT by Q. Then ISC by I zero plus 1.
Uh, please think 1 minute. Are you able to? Yes, 10 to the power minus 11. This is okay. 10 to the power minus 11 ampere.
Next. Okay.
Please correct it. Correct it. So you know the formula KT by Q,
PUC equals to Q ln
L N
ISC I naught
ISC
S1
I naught ISC plus 1.
plus 1.
Now please hold.
KT by Q equals 0.026. I can take because our
Okay,
condition
0.026 ln ISC short circuit current 7 ampere
7.
and I naught reverse saturation current 10 to the power minus 11 and plus 1. Please solve now.
And
Please uh, approximate like that. 7. This is the bigger quantity first, so forget about less,
709.
and we can convert like that. Plus 1 is
And 709.
okay, so forget 1. We can calculate like that. Yes, after solving the log
Plus 1 is 3 plus 1.
0.26 and this
One
is
step missing.
274 0.7091.
0, 1. Yes.
Okay.
Yes.
Okay, and one more question. This is let me insert one more question. Then we will solve. Wait 1 minute. Uh, I have one more question for you.
Options are same question.
Wait a minute. 1 minute. Yeah, this is the question. Now, are you able to see?
Yes, yes.
This is the question. Please solve. Yes. Yes, please.
Not visible. Yes, yes.
Uh, you know the formula. I equal I naught
Yes, sir.
exponential
Vertical to I naught, 1 minus,
alpha t, like that.
1 minus.
1 minus or
So 1 minus.
yes, yes, yes. 1 minus. Now please solve. A typical absorb layer solar cell absorb 43% light wavelength is incident from 1.8 elevation. Assume the absorption coefficient alpha is given. Alpha is given per centimeter. We have to calculate thickness in micrometer and I by naught 43%. Put this value here 1 minus exponential alpha t 43%. So we have to convert like that. Exponential alpha 20. So exponential 20 1 minus 43 by 100 or 100 minus 43 7, this is 9 4 by 100, then exponential alpha 20 equal to 0.57. Take log ln 57. Now calculate the value of log 0.57 ln 20 minus 0.562. So t divided by 10.
वो 18 कोर्स किया है क्या? नहीं, मैं तो आज वो 18 कोर्स कैंसिल हो गया मेरा भी है।
This is in centimeter.
हाँ?
Please convert in micrometer.
बहुत बढ़िया है।
562. This is in micrometer. Hello.
Okay, okay, PL course. 5, 6.
Yes. This is right.
Yes. Yes.
Okay.
Hold on.
Let me tell you how perovskite is working. This is the potential for our solar system, solar cell. You know,
Yes, yes, yes. 300 by
in 20,
yes.
2030,
In
the 56%,
2030, 500. Oh,
56%,
I think 500. Yes, 500 gigawatts. Yes. And
and working principle is also for.
what is the solar thermal? Just
Oh, wait.
previous sites.
Hmm.
Solar thing.
Solar, wind, hydro, biomass, nuclear.
Nuclear, sir. Nuclear is not renewable energy.
No. Uh, this is taken from this source. Okay. This is the structure of perovskite, FeX3, and this is the real shell. You can see.
Progress.
Are you able to
This
see?
is one cell on one array.
Uh,
Sir, yes, sir. This is array on one cell.
this is the 6 pixel of cell. Actually, six cell. 1, 2, 3, 4, 5, 6. Six array means 6 cell. And here is the working principle of perovskite. Uh, let me show.
How many materials are used, sir? Perovskite, 1, 2, 3, 4.
Yeah. Let me show you what is the structure. How is it is made? First is FTO, then spin coating, electron transport layer, device fabrication, like that. ETL coating, then perovskite coating, then HTL coating, then deposition of
HTL means
whole
high
transport
range.
whole transport layer,
Okay, the whole class.
electron transport layer. This is an NIPPIN configuration, and here is the like that material. Yeah, FTO. Here is the bottom electrode. Another is a top
Okay.
electrode. Light illuminated
Yes.
this side, and this is the electron transport layer. This is the whole transport layer, and this is our perovskite. And I will curve like that. This is the real thing in lab. So
Sir,
let yeah,
sir, one thing, sir. This perovskite cell can use on supersite or
what?
in both side, like in both side, like can again or in one side, like silicon cell.
I'm not understanding. What are you telling?
So actually, I tell you, sir. So the protons will come from one side or can use in both side.
No, no. I will tell you mechanism. Then you will understand. 1 minute. There is a working principle mechanism. Our solar cell like that. First is FTO, then ETL, ETL, perovskite, then STL, then electrode, top electrode. This first is this is known as electron transport layer. It NIP configuration. PIN if hole is FTO, then STL, perovskite, and N is electron transport layer. He or I, top electrode. Two type of configuration, PIN and NIP. Okay. When incident light is incident, then exciton is created, then dissociate, and then conduction band, valence band. This is valence band, conduction band. Electron from conduction band, energy is minimum here. You can see. So
Yes.
electron easily go here, and hole is blocking here. If hole is there in conduction band, then hole energy is higher for hole here. We can see.
Yes, yes.
So here is
They
a,
can move the
yeah, here is a barrier for hole. Hole cannot go like that. This is blocking of the hole and provide the path for electron. This is the electron transport layer. So block the hole. If the electron and holes goes like that in one way, then recombine. So recombination could can be can stop by ETL layer. Okay, then electron easily go
yes.
from the electrode respectively, and similarly hole goes up whole electron. Then by external circuit we can easily get the electricity. Okay, so the structure can be NIP or PIN. top top or bottom. I will show you PIN or NIP both. I have a both configuration. This is the PIN configuration. PIN. This is hole transport layer. P type, N type, electron transport layer. This is the absorbed material. Our perovskite, methylammonium lead. Light is incident. Then hole is collect like that, and electron is blocked, and electron goes upside to the respective level. Then we will get external circuit get light or flow of charge carrier. And here is the NIP configuration. This is an IP from, and in lab I have achieved 18.99 efficiency. Yeah. And this is the absorbance curve. Brand gap, not absorption curve here of the formamidinium ammonium lead iodide. Okay, so perovskite like that. And this is the lab. Let me show how to make solar cell in lab. Okay, 1 minute.
This lab in
Yeah,
IIT.
IIT Kanpur. Are you able to see
Yes, yes,
in video? This
yes.
is the perovskite doping of electron transport layer. We have already coated electron transport layer FTO. Then perovskite is rotated.
That's great.
Yeah, perovskite. Then we have
Electron
to,
transport plate. This is interesting.
then is anti-solvent dropping. Then perovskite coating is done. Now we have to anneal. If the film is like that black, then our perovskite phase is formed.
Wow.
So this is the annealing step. You can see black phases film.
Black. Yes.
Yeah, this
Yes.
is the perovskite. Now perovskite coating. Spiro, sorry. Whole transport layer. Top on perovskite. You can see in picture there is a black phase film. This is the perovskite coated. Now spiro dropping. Okay, so let me show one by one how to make in lab. First is cutting the glass. One side is a FTO coating, another side is glass. Then marking, patterning, then etching. We have to etch via zinc, zinc powder, zinc metal powder, and HCl, hydrochloric acid. Then you can see in picture one finger print. There is a two finger in FTO, two strips. This is the two electrodes of the cell, bottom or top electrode, FTO side. Okay. Then cleaning in lab, ozonolysis. Then ETL layer. First layer is coat on finger, two finger. Okay. This is spin coating of ETL layer. Then annealing. then perovskite coating. This is the perovskite solution you can see in picture.
Yes.
Yes, yellow light, 4 vials.
It
Then,
sounds.
then filter. This is the filter step. We have to filter, then coating, perovskite. Then annealing. After annealing, we this looks like perovskite black.
Yeah. Yes.
Then STL coating, thermal STL coating of Spiro. Then thermal evaporation. This system is thermal evaporation system. You can see, yeah, and thermal evaporation light look like. This is the gold coating. You can see yellow is, and finally device. This is the step of perovskite coating in lab. Are you enjoy?
Yes, sir.
Yeah.
Thank you, sir.
Okay. Okay. Thank you. Okay. We can stop.
Yes, boss.
Okay. Okay. Thank you.
Yes.